this is one challenge. We had a lot of challenges to come to this point. I recall that I met with Frank Holzapfel, I think it was 2014 in Frankfurt. That was the initial kickoff for our intention to tackle the very important topic of wake vortices. That is a permanent threat in the aviation. We manage it quite well. Now we manage it much better. We figured out that also safety, of course, safety is the main issue, but also capacity is one thing that has to be taken into account when we look into wake vortices with all consequences. We figured out that we, in some cases, lose capacity as we better know how to deal with wake vortices. And on the other hand, there are many ways that are already there. Frederick, for instance, that gives us capacity back. And both issues, or both these concerns, were our intention to tackle them in all these projects we have. And what has been achieved is simply great. We will see it in the afternoon. I have to excuse myself. I can be only with you until maybe 12:30. But I saw pictures of that plate. It's in a reality there, and this is very impressive. Many challenges to overcome over the years, but we did it. And at this point, I have to say thank you to European Union funding, for instance. SGU, I think there's no representative can be here today, but this is very important to say thank you in that direction. And thanks to the project team, thanks to many people here in the room, long-term supporters of that intention that we have. We have people from in the room, representatives in the room from Greece. Thanks for the chocolate. To Norway, so all over Europe is covered here in the room. And yeah, once again, thank you. Welcome to our premises. If there's any need, please don't hesitate to raise your hand and tell us. And yeah, without any further ado, I would hand over and wish you a fruitful meeting. Thank you very much.
Okay, thank you, Christian. I think, Wilfred, yes, we will start with your presentation. Here we go.
Okay, now, welcome everybody. My name is Wilfred Rauchenwarth. I'm the official project coordinator of the VLD3 project, Safely Optimize Runway Throughput, named SORT in short. I work for the Royal NLR, the Netherlands Aerospace Center, located partly in Amsterdam, where I am. I am the overall project coordinator of this project, and I work about 33 years for NLR now, last 7 years in the ATM and airport departments. Next slide, please, and one more, please. Okay, SORT, what is the project about? Essentially, we are a very large demonstration type of project, and we respond to a particular Wave 2 call of the SESAR 2020 program, named Wave 2 Improving Runway Throughput in One Airport. The main aim of the very large demonstration type of projects is to bridge a gap, the gap between industrial research and pre and deployment, or sometimes we name it pre-deployment, to increase the maturity and the technology readiness level of the solutions that we work on, or the integration of the solution that we work on. The industrial research type of projects, they bring the projects to about TRL 6, and the very large demonstration type of projects would go beyond that and try to aim for TRL 7 or even sometimes higher. And in that sense, the VLDs are a project that also provide a kind of fast track to bring operational improvements of SESAR, the SESAR solutions towards deployment. We started in April 2020. We finalize at the end of June this year. Our funding budget from the EU is about 4.5 million euros, and of course the members also contribute almost with a similar amount to that. And in the project, on a high level scene, we have what we call 3 kinds of demonstrations, and I will only briefly touch on them in the coming slides. So maybe if I can have the next slide, please. But before that, who are all inside the consortium? We see on the left side the kind of members. 81 is a kind of partnership between Royal NLR and GLR in the sense of research entity. NOTMIG is the North European ATM industrial group, and there are many partners inside, amongst which SINTEF Norway is a member of this consortium. And this project, COPANS, is a cooperation, a partnership of ANSPs, and we're happy that Austro Control, also a member of COPANS, is hosting this open day today for us, and also part of COPANS and in the project is LFV Sweden. Of course, we know Eurocontrol all, and they are part of this project as well, together with NATS of the UK, air navigation service provider, who also has a linked third party coupled to their work in the sense of the company Leidos, who works on a lot of software implementation and product matters. And also another ANSP, Skyguide, is part of this project. From the view of the SESAR European Airport Consortium, we have 3 airports available in the consortium: Heathrow Airport, Arlanda Airport as a member of Swedavia, and Zurich Airport. So those are partners, and I will now touch upon the 3 demos that are in the project in a high-level sense. The first demonstration that is being prepared and still not executed, but almost about to be started, is a demonstration of NATS and for and at Heathrow Airport, and it will run in March, so it's upcoming. It is about the combination of time-based separation and pairwise separation. At the moment, NATS already and Heathrow Airport already operate time-based separation with RACOT AU type of wake vortex separation, but we will make in this particular demonstration the next step forward, and that is pairwise separation. So the separation per type, per aircraft types are being established, and therefore the air traffic controller needs more automation support because it's no longer categories based only. You see the other partners on the left, Eurocontrol, NLR support, and Leidos also part of it. Essential is also that we work in the demonstration on minimum radar separation reduction. At the moment, NATS and Heathrow operate 2.5 nautical mile, but we will go down to 2.0 nautical miles. And the smaller you make the minimum radar separation and coupled with pairwise separation, the more tight the aircraft will be behind each other. And therefore also the runway occupancy time when landing, when the aircraft are landing on the runway becomes more and more important. So that's also part of this demonstration, where initially the idea was to have a real live trial. Due to COVID matters and other aspects, the project has decided to go to a real-time simulation with real hardware, the real hardware that is being developed for this particular demonstration. Also included in this particular demonstration is demonstration objectives that were originally coming out of the Zurich and Skyguide demonstration. Sorry, take a moment here. But that particular demonstration had to be skipped due to COVID impact, but we aligned certain objectives within the particular this demo from NATS. So that's one demonstration that we are working on. The second demonstration has already been executed last year at Arlanda Airport by LFV and supported by SINTEF as the industrial partner and producent of, say, the integrated runway sequence function hardware and software. it is all about combining arrival and departure information such that you optimize mixed mode type of operations at the airport. But also, if you don't operate mixed mode operations, but you have dependent aircraft, dependent runway of operations, you can apply this function. I'm not going to explain the whole figure, but it's all about having a very precise planning 40 minutes before landing and updating it while going to the landing phase, say up until 10 minutes before landing, such that you have for particular arrivals and departure sequence the optimum flow and the optimal sequence build. They have done a shadow mode type of trial last year, and they're in the reporting phase. Then, where we are all here for today is the demonstration that we will hear about much today by other presenters. So I'm not going to give away a lot, but it's the third demonstration that we have in the project. It's run by DLR and Austro Control mainly, and supported by other partners in the production. It's it's called wake decay enhancing concepts, or shortly plate line concept. And it's a different type of demonstration, of which you will hear more, because it's more a pre-industrialization kind of work of the plate line prototype. Now, I hope you will learn a lot of it today, and I won't tell more about it, not to waste the presentations of others too much, in the sense of duplicating the text. Okay, I'm coming almost to conclusion. What is the project result? We have the demonstrations. We are in VLD, a very large demonstration type of project. So we made a demonstration plan. Fortunately, it's still confidential, but maybe that changes in the future. We worked on a lot of SESAR solutions that I'm not all going to mention here, but the specific demonstrations worked on particular SESAR solutions. And today we are here for the solution on the plate lines. The outcome of all the demonstrations will be reported in the demonstration report that fortunately will be made public so that you can all have access to that information after the project has closed. Okay, then finally, if you want to contact us or want to know more about the project or project details, you can find us on the SESAR project website. You can find the link in the slides, and the slide where will be made available after today. You can also contact us at the upcoming Airspace World Conference in Geneva. We will have booths, both DLR and LR have a booth jointly in the 81 place. We also are preparing at the moment a presentation for the showcase that is in the SESAR Theater. It will be a combination of particular projects as mentioned here, the SWOT project, but also the ITARO project, integrated TMA and airport runway operations, and the ART airports, and now ATM runway throughput presentations will be combined, especially focus around TBS operations and arrival streaming aspects. There's in those projects several aspects that can be addressed. And that presentation will be followed by a walking tour at the NETS booth. And of course, if you want to follow us on LinkedIn, then please follow us, become a friend or member of our group, PG37 ITARO. So thank you for all for joining in such a huge community today. I'm very pleased to see so many people, both present here, physically present and online. And I wish you all a very nice day and a useful day and useful discussions. And then I hand over to, I guess, Frank for the next presentation. Thank you very much.
Okay, Frank. You will start with
FHs ganz hinten. Yeah, that's it.
this one. Okay.
If you don't need the mouse, I would be glad.
Yep.
Okay, thanks. Oh. what I want. Ah. Okay. I have to be careful. Ladies and gentlemen here in the audience and on their screens, I want to warmly welcome you to my presentation entitled Plate Lines, Physical Mechanism, Previous Investigation and Safety Gains. I really appreciate a lot that you took your time to travel to Vienna or to watch our presentations on the screen to see the achievements we could make in the last few years on the plate line principle. So this is the outline of my talk. I would like first to motivate why we are interested to mitigate wake vortex encounter risks in that particular phase of flight, final approach and touchdown. Why is that the most important part? Then I want to introduce the plate line concept, the underlying physical mechanism, briefly recapitulate previous investigations, and then come to the safety gains. These safety gains were estimated on the data that we collected during a measurement campaign here at Vienna Airport in the year 2019, and that's where this photo was taken. At that time, we installed 2 plate lines, temporary plate lines that had to be removed after the experiment. And these plate lines, as you can see, consisted of wooden frames covered by truck tarpaulin and could be folded up and down, and they were held by ropes. So a simple solution just for that campaign. Finally, I want to introduce several use cases that we have developed in order to translate these safety gains in potential runway capacity throughput gains, which obviously would be needed such that an airport or an ANSP could be convinced to really install the plates at an airport. I also don't want to conceal that we were lucky to be winner of 2 awards. For the Maverick Awards, we were at least finalists, and the ATM Awards, we ended up on 2nd place. So here's the motivation. I guess all of you are very well aware that long-lived counter-rotating vortices are formed behind aircraft, and that these vortices pose a potential threat to the safety of following air traffic, and that they also limit the runway throughput capacity of major airports. Maybe you are not as much aware that most encounters occur during final approach, as is also shown in the statistics on the right, which is showing reported encounters by NUTS during the years 2000 to 2004. And you can readily see that in the lowest height range, which reaches here up to 500 feet above ground, most encounters occur for inbound traffic. But why is that? So along the glide slope, vortices always induce each other at descent speed. So along the glide slope, they can descend below the flight corridor. Also, crosswind will affect the vortices laterally. There are a few atmospheric situations where this descent speed is impeded. This is, for example, thermally stable stratification or updrafts of convection or crosswind shear. But all these phenomena also reduce the lifetime of vortices. This is very different in the ground. Here you see a large eddy simulation, different perspectives of vortex behavior where the background turbulence is contributed by a weak headwind. And left below, you see the vortex trajectories the best. So when vortices approach the ground, of course, they can't continue descending, but they first diverge and then rebound. And this divergence and rebound, but also the decay, is related to the formation of secondary vorticity on the ground that then detaches. Secondary vortices are rotating around the primary vortices, leading to the rebound and the decay. Now, if we, in that situation, have on top a weak crosswind, here in this example from the left, you may end up with a situation shown on the upper right. Here you see the 2 vortices in an NTU, and you can see that the upwind vortex really hovers at the position where it was generated, close to the ground, and that here the risk to encounter vortices is relatively high. On top of this, look at the sketch on the top left. you see that the crosswind shear has the same rotational direction as the secondary vortex of the downwind vortex. That's why this vortex is stronger, detaches first, and the downwind vortex we don't care about, which is blown away, decays faster. But this upwind vortex causing the decay, secondary vortex, the decay of the upwind vortex is weakened by the shear. So this makes the situation a little more complicated. Below you see trajectories for different crosswind strings, on top for the left vortex, below for the lee vortex. And here the red curve is the critical situation. This is for a crosswind on the order of 1 meter per second, a little less. The vortex descends, rebounds, and then passes really the runway center line at a flight altitude where the next aircraft may pass. So this is also something which is not new. This is known in the wake vortex community. So when wake vortex separations were determined for the A380, still all phases of flight were considered and measurements were done. But already for the B747-8, they very much focused on a flight altitude like this, 60 meters above ground. And also the recategorization initiative initiated by ICAO and in the first phase implemented in USA and Europe, they also focus very much on vortex evolution in ground proximity. So here we really have the bottleneck of the whole flight. And then the plate lines don't only look at this most critical phase of the flight. Imagine a pilot also doesn't have much time to recover at this at low flight altitude, but it also considers the situation where vortices will live relatively long and remain in the glide path. So this is, I could say, the most critical part of the whole flight there. The wake vortices are supposed to reduce wake vortex lifetime. This brings me to the plate line concept. Plate lines are a device accelerating wake vortex decay in ground proximity, the bottleneck with most encounters. They consist of 8 vertical plates installed under the glide path, as you can see on the photos. A plate line is a passive, cost-efficient, robust, and safe device, contains no movable parts, and requires no electricity. So what are the plate line benefits? If wake vortex decay is accelerated, we will have less encounters, we will have increased safety, and we will have less go-arounds caused by encounters. Next, plate lines may be used to compensate the increased encounter rates that could be brought along by recut EU separations, in particular by pairwise separation, stage number 2, because recut EU follows the logic that strong encounters are avoided by optimizing the separations, but that less critical encounters can occur more frequently. And here, as we know, pilots, airline association unions, or airlines, they might be not fond of that increase. And then in the next step, there's also the potential for capacity gains by reduced aircraft separations made possible by the accelerated decay of the plates. So what's the physical mechanism behind the plates? Here again, results of numerical simulations. So if the main vortex here on the left approaches the ground, it introduces a secondary vortex at the ground. But if we have a plate, it very early triggers, as we say, omega-shaped secondary vortex. So this is like a ring vortex, and this actively induces itself a velocity towards the main vortex, like a smoke ring of a smoker. The main vortex, with this rotation, will wrap the secondary vortex around the primary vortex, and then we have 2 spiral-shaped rings that again induce in themselves a propagation speed in both directions. The disturbances propagate along the vortices and accelerate vortex decay in situations where no external effects like turbulence do the job. So these are investigations that we did over the years since the idea of the plates came up already in the year 2008. They have been further developed and validated, and we started with towing tank experiments shown by the video on top. I see the 3 animations are a little bit demanding. I hope you can see something on your screens. So on the top, we have a water tank, a small aircraft model is towed through the tank, and the vortices are visualized by dye. We have here on the right an obstacle. I hope you can see it. Another one here, but you can certainly see that when the vortices approach this obstacle, disturbances are traveling in both directions. Then we did really a large number of high-end computational fluid dynamics simulations. The example is shown here in the middle. This is a so-called hybrid simulation where we also simulate the detailed flow around an A340 aircraft in high lift configuration with individual flaps and everything. So the vortex roll-up is really considered in detail. This is a final approach in the landing and flight over the plates. And such simulations were used to optimize the shape, the dimensions of the plates, their separation, and also the robustness against wind and turbulence, but also for the effects for aircraft of different sizes. Then the year 2013 saw the first real flight research experiments at DLR premises in Oberpfaffenhofen, where the DLR research aircraft Halo, a Gulfstream G550, produced the vortices. And the vortices were made visible by red smoke and fog. And I hope you can see a little bit. The animation is not running smoothly. But you have to imagine that this aircraft has a wingspan of the order of 30 meters. And later on, you can see here people. I don't know whether you can see them, but the sheer size of these vortices of a not so big aircraft really make clear that if a big aircraft generates this usually invisible vortices, they can pose a problem for follower aircraft. So here are a few photos, some impressions from the Vienna demonstration campaign in the year 2019. Left, the installation of the plates, which were fixed to the ground with ground anchors. I mentioned already they consisted of wooden frames covered by truck tarpaulin. They could be folded up and down. And we also at that time had a visitor day. So I hope we will have a similar photo now, not with a temporary plate, but with a plate that can really installed at an airport to stay and do the job of mitigating wake encounter risks. So a little more information about that measurement campaign. Here you see a top view. On the lower end, you see the threshold of runway 16. Maybe somebody landed there. We came from 34 this morning, so from here. And a first plate line was installed at about 400 meters from threshold in front of the localizer, consisting of 8 such plates. Each plate has a height of 4.5 meters, length of 9 meters. This dimensions are kept, they didn't change. And at the distance of 340 meters, there was a second plate line, again, the red dashes. And we were operating Leosphere LiDARs. We had 3, but 5 LiDAR measurement positions, L1 through L5. And we have, Leosphere is now with Weisslar. We also have somebody from Weisslar here. I'm glad about that interest. So we were measuring directly above the plates, positions L2 and 4, in between, then between the touchdown and the plate, and also further up. And we had a number of other meteorological information that I don't explain in detail now. So what we got, we collected like 9,000 approaches, but from those we could evaluate only a relatively small part. The numbers are shown below, like 250 approaches with and without plates lines, respectively, that correspond to roughly 600 individual vortex pair evolutions with and without plates each. And you end up with such scatter plots, vertical position against time, vortex evolution in space, and circulation decay. That's the strength of the vortices. And obviously, you see here with plates, we have green and blue dots, without plates, red and magenta. And obviously, you don't see so much because there's a manifold of wake vortex behavior. You can, in the decay, can see the blue and red vortices live shorter than the others. But we really had to develop an evaluation strategy to find numbers that really describe what's happening. And I want to go through these. These were intended to have good quality and also to make sure that the data is statistically significant. So first of all, for processing of the LiDAR data, we used an interactive processing algorithm, which also is time consuming, delivers very good quality, but explains that the number of what measurements that we could process is limited. And then we inspected all the measurements and excluded obviously erroneous data. Then we defined a safety corridor. So we consider only vortices within a safety corridor with dimensions plus minus 50 meters from the runway center line, because vortices attracted far from the aircraft away, they don't play a role for safety or capacity. This corresponds in the end to wind effect. So we considered only situations with weak crosswinds below 1.5 meters per second, but we also had a headwind threshold. For this, it's important to understand that when the aircraft touches the runway, vortices are very much disturbed. So-called end effects are generated that disturb the vortices, propagate against flight direction. So if you have a strong headwind, these disturbances reach farther and accelerate the decay. That's something we also saw in our data very clearly. So we evaluated different aircraft separately, but also to also be able to combine them. We normalized the wake vortex data, then it's dimensionless. It can be plotted together for different aircraft types. And then to quantify circulation reduction, we considered only vortices where the last measurement location is situated within the safety corridor in order not to have a systematic bias in the data. And for the lifetime reduction, we don't need that stringent requirement. There we evaluate all vortex pair measurements within the safety corridor. And to make sure the statistical significance, we use the Wilcoxon ring sum test. So, and with such measures, we could develop curves you see on the left, which are much clearer. The plate effect is much clearer. What you see here is the vortex age distribution in different vortex strength ranges. So while the vortices are straying, the curves with plates up and down almost perfectly collapse. And with increasing decay, they deviate more and more. And the median here shown, the vertical line, of course, deviates much more with the progressing decay. So on the right, there's a list of the key findings I would like to present today. First, plate lines cause wake vortex lifetime reductions comparable to a high turbulence scheme. So I tried to explain in the beginning, these plates are made when we have low turbulence, when we have the longest lift or reasonable worst case conditions. That's a term which is also used by Eurocontrol. And the plates, they act like they would make some turbulence which is not there, but which is efficient in destroying the vortices. And we also found a single plate line is almost as effective as two plate lines. So we currently think one plate line should be sufficient. We don't need the second one. It was very difficult to find the propagation speed of the plate disturbances. Currently, we think it's about 8 meters per second. We still have to look a little closer what that means for particular airports. And the main messages are the last two. So the wake vortex lifetime is reduced by 22 to 37%. And this depends on the aircraft size, which is at first glance kind of surprising. But if you imagine that the flight height above ground is defined above the plate. And for bigger aircraft, the vortices are bigger, such that they reach closer to the plates, and the disturbances by the plates are caused earlier and more efficiently. And of course, it's very good for us that the plates are most efficient for heavies, which are the main problem. We can express that differently. We can say that the vortex circulation is reduced by 50% for a time separation corresponding to medium behind heavies. So this brings me to the use cases, and the use cases we envisage are all combinations with existing or future separation schemes. And you may not be aware of all of them. That's why I want to briefly introduce these separation schemes first. So RECART EU optimizes the minimum wake vortex separations by classifying aircraft types into 6 categories, and not based on the maximum takeoff weight like the ICAO scheme, but based on a selection of relevant aircraft parameters. That's RECART phase 1. RECART phase 2 extends the scheme to individual pairings. PWS stands for piecewise separations of leading and following aircraft. REDSEP is a scheme that also was developed here in Vienna, and it allows the delivery of applicable separations between medium-medium pairings and medium-heavy pairings, not only at the threshold, but already at 1.5 nautical miles from runway threshold. Under IMC, instrument meteorological conditions, under VMC, they do that anyway, but under specified wind conditions, only for a certain amount of headwind. We talked about headwind before. And then finally, dynamic pairwise separations, also known as recut stage 3, allows the reduction of aircraft separations depending on the prevailing weather conditions and the resulting wake vortex behavior. For this, you need a wake vortex advisory system like the system that DLR developed. That monitors and predicts weather conditions and the resulting vortex behavior and translates those in separations. So this is a sketch for the use cases, 5 different use cases. They all start with the installation of a blade line. And if you just do that, you have an increase of safety. If you want to see potential capacity throughput gains, you can combine it with recut EU or recut EU pairwise separations, just the schemes. So recut EU is already operating for several years at several European airports: Toulouse, Paris, London Heathrow, Leipzig, Halle. Pairwise separations will probably be released by EASA this year, and London Heathrow plans to install it the first. In the safety case, I said that before, or the principle is to avoid strong encounters, but as you reduce separations, the number of encounters is increasing. And here for pairwise separation, the guess or estimate is this could be 60%. And we think this may limit the acceptance. And if you combine the introduction of pairwise separation with the plate lines, you would have both benefits. You would have substantial capacity gains and safety gains at the same time. Here is a rough estimate of capacity, which is landings per hour during peak demand. And this is the Vienna traffic data. We use 1 year of traffic data. Christian Kern helped me how to use that in a meaningful way. And you see that recut EU can also already increase that number by 3 landings per hour, pairwise separating by 5. These are substantial numbers. And if you can get that without increased encounter frequencies, I think that's a good message. And that would be available at quite short time. Looking further in the future, we could use the method developed for recut EU, which considers the decay of the longest lived vortices, the so-called reasonable worst case decay curve. This is modified by the plates. The decay is faster. And then we can use the same method and come up with 2 additional landings per hour. For this, we then have to see whether there are other bottlenecks. If we reduce separation close to the ground, we have to see what's happening out of ground effect. And this will be shown in the talk of André, that for some aircraft pairings, we may have limitations which are not yet considered in these numbers. Then the REDSEP scheme, there the idea is that we don't need the wind threshold. So REDSEP only works for headwinds, which have to be monitored and predicted. The procedure has to be switched on and off. So we think with combination with plate lines, we can simplify the procedure by making it independent of the wind. You could use it all the time, and you don't have to switch on and off and monitor the wind. And then dynamic pairwise separations. Here, the capacity corresponds to, so when the weather prediction is favorable, you can separate the aircraft at minimum radar separation. Here, the assumption is 2.5 nautical miles. And so while this is happening, you would have the maximum possible capacity gains of about 10 landings per hour. And as most encounters happen, as this system is mainly limited close to the ground, plates may also help to use this dynamic pairwise separations more frequently. So this brings me to plate line flags. My conclusions. I think I could convince you that plate lines increase safety and potentially runway throughput capacity, which we will see in the next talks. It's a passive, low-cost, robust, and safe method. As we will see in the next time, plate design is ready for installation at an airport. And the lifetime reduction of long-lived vortices ranges from 22 to 37%, depending on the aircraft size. Circulation reduction is by about 50% for a typical medium behind a heavy. And we have different use cases which lead into the future, different time spans, but with up to 10 additional landings per hour during peak demand. And, oh, okay. So this was obviously not really the latest version, because I also wanted to show you the number of scientific publications that would be available for interested readers, and also the patents. The method is patented in a few countries. But here I, of course, also have to thank not only the team and you, but also for the funding from SESAR, the SWORD project, the PJO2 before, and everybody who made that possible. It was quite an endeavor. Christian Kern mentioned a few things already, and in between we really had to be a little tough to come where we are today. But we're all happy, and we made friends and made a team. And maybe in the future we will all also make more capacity. I mean, that's the goal and the big wish. So I think we would have time for 2 or 3 questions. This at the end of my talk. We have discussion time after the 3 talks, but maybe 2 or 3 questions would be possible now. Thank you for your
from online, of course.
Yeah.
We check it.
There's somebody online. If not, we just go ahead and discuss.
Yeah.
Frederick.
Good morning, everyone. I was wondering about something you mentioned, that you made the assessment with 2 lines, 2 plate lines, in fact, but you said that you found that maybe only 1 could be enough. On the other hand, you explained that typically so far we focused risk assessment for wake turbulence encounters with this what we call reasonable worst case location, which is corresponding with the near ground interactions and the 1 wingspan altitude. And clearly in the aircraft fleet we have for heavy aircraft this one wingspan altitude is around 60-65 meters. For medium aircraft it's smaller, it's 35 meters. For A380 it's 80 meters. So how can you then ensure that with only 1 plate line you can cover this range of altitude and location to the same extent? And if not, then how to prioritize the locations against different altitude?
Yeah, this is really one or maybe the most critical aspect that Frederick puts on the table. So as I showed you in the sketch, we were measuring in 5 measurement planes. Unfortunately, the scatter of LiDAR data is substantial, and the plan was really to see how the disturbances propagate from one plane to the other. And this was not so easy, and also in the end, for the measurement plane L5, the weather conditions were not that we could have enough measurements. So we developed more advanced methods to estimate the propagation speed. And I showed you these 8 meters per second, which were not so easy to find, which I think are quite credible now. And now the next step to see what that means for a particular airport has to be seen for every airport individually. We're talking with Zurich. People are here from Zurich Airport. They are thinking about moving the threshold because of other measures farther away. And then we really have to see, this is current research, how far can the plate be away from the touchdown zone to cover the whole range. What I showed you, this analysis is an average value of all the behavior that we found in this relevant place that cover. I mean, we have different aircraft sizes. We have here A320 to A380, also smaller ones, but we focused on A320, B763, and 777, B777. And yeah, I think if we really want to have one use case, it's 3 to 5 with additional reductions on top of pairwise separations, for example. We have to do more measurements to really show whether these estimates are really true at a particular airport, which has a little different topography, different positions. I think at least for the first installations, we have to do that job. And what we are doing now, what we are presenting now, is not sufficient to really write down a safety case and submit it for approval. I think use case 2, I hope I made that clear, that something where the plate benefits with combination of pairwise separation with plates. That's something which could be done maybe at the end of this year, and which I think would be very good to increase both capacity substantially but also safety and reducing counters. And for that, you don't really have to know the details. You say you have an average and substantial benefit on average. But if you really want to get closer, I think you have to have a more clearer picture than we have now for benefits. Okay, I think that brings me to the next talk of Grigori Rothstein, who worked on the plate design that we will visit in the afternoon. And yeah, I'm looking forward to the photo. Everybody of you, Christian Kern won't be there.
Photo
Can we
Photoshop?
Photoshop? Can we Photoshop you?
Sure, have the opportunity in the near future to visit the site.
And of course, the people on the screens, we don't take the camera along on the side. You will see a photo of the plate design in this talk now.
It's proven it's there. It's not Photoshop.
Okay.
It's reality.
So hello everyone, my name is Grigori Rothstein. Yeah, nice to see you all here. Thank you for coming. It's really a beautiful sight from in front of here to see so many people interested in the plate lines. So today I will talk about the technical plate design for permanent installation. Frank has already mentioned that the plates are ready to be installed, and that's the main point that I would like to get across with this talk, to show you that actually we have a design that is ready to be at an airport, and also how it is incorporated into the SORT project, because as Wilfred already described, it was the question of a pre-industrialization project for this plate line product. So let me start with the motivation. As Frank has mentioned already, the measurements at the measurement campaign in Vienna in 2019 were very successful, and they supported further development of the plate lines. But the design that we used for that measurement campaign was a temporary design that you can see here. So it is just a wooden frame with a truck tarpaulin between it, consisting of 4 such segments, and also with ropes attached to the ground. And it was sufficient for our measurement campaign to show that the plates are effective, but it is not something that can be permanently installed at an airport, because it only can withstand relatively weak crosswind. It needs full-time supervision, as we did during the measurement, and it has to be folded up and down manually when it's not in use. And of course, the lifetime of the plate is too short for it to be really installed at an airport and in use. And that was the main motivation for us to say, okay, we are happy with the results. We have proven that the plate lines are effective, but to actually install them at an airport, we need a design that can be there permanently and is easy to use. So with this goal in mind, we actually went through a very rigorous and very systematic design process, as you can see here. We started with a requirement definition. We went into a pre-design where we looked at different options for us, how this plate could be designed. Then we went into detailed design and really developed the plate. And in the end, we went through the industrialization, where we actually produced all the necessary documentation that we need to install a plate at the airport. And I think my main message today, what I'd like to get across, is that we really looked in detail at all the requirements and all the design options that we have, and we have a product today that you can really trust to be at an airport. And I will go just through all these steps in my talk, so you can actually see what we did and how we progressed. So we started actually with the requirements definition, and here we wanted to really have all the necessary requirements that an airport could have for such a plate line. And that's why we collected from different experts, mainly our partners in Austro control, but also our own experts. We collected all possible requirements that we could think of and that seemed sensible in a requirements list. And then this was actually, as Wilfred has described, this was in April 2020. So we made our first experience with online meetings. We met for an online workshop during the start of the pandemic. And we grouped all the requirements that we had collected into these 8 main categories. And then everybody who participated in the workshop had the possibility to vote on the importance of this category, so that in the end we came up with an expert score on how important each category for the design would be. And just to give you an example, when we say, for example, the category effort, it contains on the one hand, the effort to actually manufacture and install the plate line, but on the other hand, also the effort, for example, for maintenance and also for mowing the lawn around the plate line. So we actually looked at all the details. And the 2 most important ones I'd like to show you in detail. And this is really a challenge for us in the design process, because it's a little bit contradictory what you want to achieve here. So on the one hand, the plate has to be stable and has to withstand any winds that you can expect, and also any loads that are generated by the wake vortex. But on the other hand, you can see here it needs to be frangible, so that in case of an aircraft collision, the plate will be destroyed. And there's actually an ICAO rule for this. So I just took an excerpt of this. These are not all the details that it needs to comply with, but this is it just illustrates how this would be tested and how this works. But as you can see, on the one hand, on the left side, you need to be as strong as possible, and on the right side, you have to brake as easy as possible. And that was really a challenge for us to develop a design which actually can comply with both these requirements. And then, of course, what we did to find the possible solution was to look at many different concepts and to try and evaluate which would actually be the most, the one that works the best. And for this, we actually went first with a morphology analysis. So we looked at different design areas and we looked at different possibilities how to solve this. So, for example, we said, okay, we have a certain amount of masts for the plate to consist of. And then we could vary how many masts we use. And then based on different design areas and different solutions that we could develop, we actually developed a long list of different options that we had for the design of the plates. So for example, here you can see a design option where we have 5 masts and they are covered in between with truck tarpaulin. On the other hand, we had an option where we had only 4 masts, but it's covered not by truck tarpaulin, but by actually panels, so hard panels. And we also used ropes. And as you can see, we even considered possibilities where we just use some kind of tuja plant edges, to have the plate shape. And also maybe one thing that we also considered was, can we actually build a plate that is strong enough to be standing upright all the time? Or do we have to have a movable plate, which, for example, can fold to the ground, but in an automated manner? And we looked at all of this. And to decide, okay, which one of these is the best, we cannot develop all of them in great detail. We actually, again, looked at an expert workshop and had the possibilities to rate. Each expert rated each design according to the design criteria that we had defined before. And that way we came up with a score for each of these design options, and we were able to select the most successful ones for further development. So now I could go through each of them and show you in detail what we did, but to spare you a little bit of time, I can show you at least for 2. We actually did a detailed analysis and we saw that, yeah, this will probably not work. And on the one hand, it's because of low stability. So with only 4 masts, we were not able to make the tarpaulin solution work. But on the other hand, also we had a movable design, which we already considered that it could be too complex. And it turned out that, yes, it is, from the engineering point of view, a very interesting and very good solution. But if you look at the complexity that you have to install at an airport and make it frangible and make it work all the time, it was just too much. So we said, okay, this will not work in practice. And something that we actually learned along the way for the plate design is the big advantage of the plate lines is that they are very simple and passive, and they don't really have much complexity. And that's what actually makes them possible to do. So if you start with a high complexity solution, this wouldn't have worked. I have been talking a lot about the masts and also about the panels, and I would just like to show you a little bit of the design solutions or these design elements that we use. So on the one hand, you have these latex masts, which you can see here. These are actually frangible masts that are that have this frangibility certification and that are already used throughout the world at different airports. For example, for ILS, but also for different applications. They are certified for frangibility, also certified for ILS conformity, and latex have also a big experience to work with also specialized solutions. So not only a standard mast, but also in a more complicated and specialized configuration. Then on the other hand, we looked at alu-core panels. So these are basically honeycomb core aluminum composite panels, which are very light, but still strong. And that was for us a concept to ensure frangibility. I will talk about this later on. And they are used mostly in building facades. So they are actually an element from architecture, but this also means that they themselves are able to withstand wind forces. So this was a big plus for us. And last but not least was also the truck tarpaulin, which we had a little bit of experience from the design of the temporary plate. And we also considered that as one possibility, probably also a cheap and simple solution for us. Going into the detailed design, I showed you that we selected two designs that we wanted to develop in detail. And here you can see one of them. This is the 5 masts from latex that I just showed you with the truck tarpaulin in between. We actually developed this kind of connector, which can be connected to the mast. You can see it a little bit here also on this picture. And then in the center, this connector is then through turnbuckles connected to the truck tarpaulin. And you can use the turnbuckles to ensure that the truck tarpaulin is actually stretched even when there is no wind. So this was one solution. And the second solution, which was just 4 masts, but with panels. And you can see also the CAD drawing of this here. So it is similar, but instead of the truck tarpaulin, and instead of 5 masts, it uses 4. And instead of the truck tarpaulin, we actually used these honeycomb core panels. And maybe one detail, you can also see that the panels are on different sides of the masts. We also developed a very similar connector, which also is connected to the mast. And this connector, so the panels on the back side, they have this kind of hooks. And these hooks can actually hook into the connector, as is animated here. I think that is more or less clear to see. And then what we did with these two designs, we actually looked at a finite element model. And with this model, we could analyze internal stresses, we could analyze displacements, we could do a very detailed analysis of all the stresses in the masts, of all the stresses in the tarpaulin, all the panels. And we actually saw, okay, for the 5 masts with the tarpaulin solution, there is a safety factor of 1.5 that we reach. So this is something where, so the safety factor you can actually look at is what stresses do we actually see during the maximum loads, and how far away is this from the allowable stress. So if you have a safety factor of 1.5, this basically means the stress could raise by the factor of 1.5, and the material still would hold it. Okay, so this was okay, let's say, from an engineering point of view, but we actually would have liked a higher safety factor for our installation. And we did the same, obviously, for the panel solution, and here we have a higher safety factor. But of course, the question of frangibility, that was one issue that we had to tackle, because with the truck tarpaulin and with the certified frangible masts, it's clear that frangibility is ensured. But with the panels, we need to make sure that the panels don't actually make the masts more sturdy and don't affect their ability to be frangible. Yeah, but based on this and also with the frangibility concept that I will show you on the next slide, we actually said, okay, this is the solution that we will go with because it has a higher safety factor. It is also visually, it looks better. It also has a higher longevity. And with the safety concept, it actually works really well. For the frangibility concept, you have to bear with me because this is now a complex slide, which I need to explain in detail. So basically, the design, as I said, is made with hooks. So if you look at this is the top view of just two masts with the panel, and then you have the hooks which are attached to the connection bar. And the hook are actually attached from one side. So this means on the left side, the hook can move to the left, but it cannot move to the right because it will hit the connection bar. That's one side. The other side is mirrored. So that means that basically the hook here can move to the right, but it cannot move to the left. In combination, this means that during normal operation, the panel cannot go anywhere. It cannot move to the left, it cannot move to the right. And that's the normal operation. And also the wind can only bend the panel, but it cannot change the distance between the two masts. So that means it will work also during normal operations. But then in the frangibility case, where you have an aircraft actually hitting the plate line, what happens is that the mast is frangible, so it starts moving. And that way, the distance between the two masts is getting lower, and the hook on the other side of the impeding aircraft is actually falling off of the bolt. And that means that basically the panel will just fall off and will not affect the frangibility of the masts. Okay, this is more or less understandable. And of course, another important factor is that the panels themselves, they are lightweight, so it's easy for the aircraft to move the panel away. Okay, and with that, we also looked at using FEM at all the details. So we looked at different wind directions. We looked at, we made sure that the panel can actually take these loads, that all the masts can take the wind loads for both wind directions. We also looked at just the connector. We looked at the hooks. We also made sure that actually high wind loads are not able to lift the panel of the hooks. And we saw that this is not happening under high wind loads, but still we added a redundant holder at the top of the mast, which holds down the panel, the top panel, and then the top panel holds down the lower panels. And that means that this has a double insurance that the panels will not go off the hooks. Yeah, and with this we were very happy because now we have really a working solution that we can use. And so, as you can see, we produced drawings and CAD models for all of this. So we have 4 latex aluminum masts in the final design with 9 alucore panels. The panels are attached to the masts by this hook solution that I presented to you. And then you have also on the inner side of these 2 inner masts here, you have this kind of cover panels, which prevent the wind from going through the plate. Yeah, and we produced CAD models for all the parts. We produced assembly drawings, production drawings. We have a list of all the parts that need to be produced. We have an assembly instruction for the whole structure. And we have a detailed technical documentation documents, which also includes all the calculations that you need and all the design details, and also the history of how we came there. Just to have an impression, also here you have the drawings of the assembly of one panel. So you can see here the hooks on the back side of the panel that will be used to attach it to the mast. And on the other side, you have the mast where you can see the attachment bars, and they are also at defined heights. And you have also drawings with details how to attach the attachment bars. Okay, so with this, I just want to also talk a little bit about the foundation. We actually developed two different solutions for the foundation, but the solution that you see here in Vienna at Rauchenwarth is where we opted for one single foundation, which was filled on site, and we used the foundation kit for the mast, which was developed by Latex. And basically, the foundation kit it consists of 4 rods that are inserted in the foundation when it is created, and then the mast is screwed onto these 4 rods. They go very deep, so this actually can take also all the wind loads that are needed. And one thing that also may be interesting and important is that if you have grass next to the plate, the mower for the grass can actually go over this, and you don't have to manually trim the grass close to the plate. So yeah, that's also something that is useful in practice. Going forward, we had an expert review process of all the calculations that we made, and actually by Mr. Gruszkiewicz, who is not here today, I think.
He will join us later.
Okay, great.
On site.
So he will be here. He looked at all the designs that we made, all the calculations that we made, and he made also some suggestions and some clarifications that he needed for us to adapt the design. What I showed was already with these adaptations, but I just want to emphasize one thing. It's maybe just a small change to the connectors, because as you can see, we had a small step here at the connectors, which was meant to transfer the force between the panel and the mast. And what we did then, based on the recommendations from the review, was actually to remove this step, and now the force transfer is actually here by friction. But this allows us during assembly to move this connection part to the left and to the right, and this helps to counteract any tolerances that you have during assembly. So that really helps the design, and also helps for the tolerances of the foundation to not have as high a requirement as they otherwise would have. So yes, we actually implemented all the recommendations by the reviewer, and also we had a second, let's say, a short review of the implementation, where we actually got the okay from the reviewer, who said, yes, you implemented everything that I wanted correctly. Okay, so that was the next step, and then just a few images that Alexander Flo made during the construction. So first I have to say the plate line was delivered as a kit by Latex, led by Gunnar Bendingsen. So thanks Gunnar a lot for this. So not only the plate was delivered by Latex, but they also did a lot during the design process and really helped us. So this was a really big help for us to achieve the goals here. So thank you, Gunnar.
Thank you.
And then we also worked very closely, not only during the construction, but also previously during all the whole project. And Mekan, you already said it was a long time ago when you first met, and we were always in cooperation with Austro Control. But I would like to point out that Alexander Flo and Johannes Schwarzenbacher, they have really done a lot to support this project, to bring it forward, and including organizing the construction of the plate lines, and also the construction of the foundation, which went surprisingly smoothly for me. I was a little bit nervous when this happened, and I can say Frank and myself, we actually booked a flight to the construction. And when we arrived, everything was already done in one day, much faster than we expected it. So we were very happy, of course, that this went so smoothly. But on the other hand, we missed all the action. So I want to say thank you to Johannes and Alex for doing this. So it was really a pleasure working with you. You can see the process really indicates very well how this was constructed and how this went forward. And we also had a lessons learned document from this, and we also already adapted the design with some minor things that we found during construction that really helped us to improve even more. And we will have a second plate line prototype at our site in Oberpfaffenhofen, at the DLR site in Germany, where we already incorporated these changes. So these are just minor, but these are something that really will help in the erection process and also maybe in longevity. So yeah, that was also a very good experience. Yeah, summing up, this is the final product. You will see it later today. Really nice, and as I said, my key message is it's ready. It's ready for permanent installation at an airport. It's compliant with airport requirements, which we collected in a very rigorous form. It's very documented and reviewed in detail. We learned that it's easy and fast to erect. And I learned only recently that it's already been tested by a winter storm. So it's still there, and this photo is about after the storm, so it has also proven itself in practice.
That's good.
All right.
With that, I say thank you for your attention, and yeah, I'm happy to answer any questions you might have.
Thank you. Just one question. How deep did you have to go into the soil for the foundation?
It's
Do you know
more than
that?
1 meter. It's 1.4, I think.
Is that really necessary, or is it kind of minimum, or is it has a safety safety kind?
1.1. Yeah,
1.1.
I have it as a backup.
Okay.
Yeah, so it's 1.1 meters deep, and yes, it's proven necessary because it was part of the review. So
Okay.
we actually we designed it even a little bit less, and it was adopted by the reviewer. So yeah, I think today it's as small as it can be in terms of.
But we also learned that prefab foundations may be simpler. You can also buy prefab, and that would make it probably faster and definitely much cheaper. And they are smaller and
they are
also
smaller.
sufficient.
Thank you.
But you know, when experts come, they want to be on the safe side. Things keep growing.
That's why I asked.
Yeah.
It's a safety
Yeah, but
margin.
there's of
inside.
course a safety margin, so
Yeah.
you can be sure that nothing will happen to this foundation.
What were the design wind limits for the panels? They're designed to withstand winds up to what?
Well, they are designed to withstand winds basically according to the same Eurocode standard that we also use for the whole plate. I didn't really mention it, I just showed it briefly. So, sorry, just go back. So, this is a European wind standard. And I wrote down that the base wind speed is about 100 kilometers per hour, and gusts are up to 180. But this is not really precise because it's a more detailed process. You cannot really say it's just one wind speed and that's it, because it has to account for gusts, it has to account for aerodynamics of the plate, it has to account for the area where it is situated. So this is just a rough, let's say, estimate what it comes down to, but in detail you go through the norm.
And during the storm, we had 60 kilometer per hour wind and gusts between 90 and 100 kilometers per hour. And it's still there.
And the masts are designed for wind speeds up to what is it, like 62 meters per second. That's like the force of jet blast, right? Yeah.
Maybe a reaction to that, because maybe if you have these strong winds or gusts, in fact, the effect of the decay plate is maybe less of interest, because anyway you have the wind effect on the decay. So in that case, maybe you can consider to have something foldable that. Something foldable, basically.
Yes, we actually considered that. Yeah. We looked at it, but what we saw is that we cannot really design this folding mechanism in a way that it's worth it, because you can then use a smaller amount of masts or cheaper masts or smaller masts, but the mechanism itself is pretty expensive. Or let's say we did not really get quotes for it, but it's complex. Yeah. And I think it will not be worth it to have this kind of mechanism. We considered that in detail and we really looked at it, but I think it doesn't work out.
And such mechanism you have to maintain.
That's true.
Of course, but again, you remove the other challenge of the strong winds.
Yeah. So I think we can say today that we have actually weighted these options if we would like to have the high wind requirement, or if we would like to design this kind of movable mechanism. And the high wind requirement is easier to fulfill than to have this kind of mechanism. But that's not clear from the start. That's something we learned during this process.
Did you, for the new implemented design, not the latest, but the one you implemented here, also do the frangibility test again, or?
We did not do the test, but we have the concept, and we think that as the masts are tested and certified, we think that this will work.
Okay. So same principle as
yeah,
done before.
Exactly. So it uses basically the frangibility of the masts, and the panels. It makes sure that the panels do not make the masts more sturdy because they're not really connected.
Yeah. And you mentioned in your finite element analysis, you also have to do calculation for crash impact or aircraft impact to get the plate shifted out of the bolt.
Yeah. So
this is the direction important of the impact. Is that?
So I have to say that for the finite element analysis, we considered the wind forces, but we did not consider the crash with the aircraft. So this is not the finite element analysis. This is the frangibility concept of the design.
Yeah.
And I think the direction, of course, it is important, but the direction that we are dealing with is the more difficult one, because the aircraft actually.
It's the most critical.
It's the most critical one.
Okay, thank you.
I remember at one point in time we questioned whether or not in high wind condition where vortices have no effect, whether or not these plates can create whatever due to the change direction of winds for any effect of potential problem for landing aircraft. You know what I mean? Mm-hmm. Is that something you had in mind? Or?
We considered that, but we think it's not really relevant because what the high wind, if you have such a high wind that it generates, that the plates in themselves generate such strong vortices that they are relevant, they are also blown away. So it's not really.
So this is
a
not
relevant case for us.
Any current that goes straight up.
Exactly.
Okay, it's not the case
because it takes some time to build up also such a vortex.
Thank you.
Can you give us an idea about the investment costs, of course? Nowadays, everything needs a positive business case. Second question, was it paid by both Vienna Airport and Austro Control, or how was it distributed?
Maybe you can answer about the distribution of funds.
So it's funded by SESAR, so we have a very high rate of getting back the investment, and Austro Control is the only partner here in Vienna who's participating with the costs. So we have to pay 30% by Austro Control and 70% is paid by SESAR.
So there was basically no invest by the airport itself?
No, not yet.
I mean,
nice model.
To make that clear, we have installed one plate and not a complete plate line now. And it's also not on the airport, it's just a demonstrator.
Yeah, costs.
Yeah, in terms of costs, I mean, this is also one point. We have installed one plate, and of course it's expensive because it's the prototype. So it's really not so easy to extrapolate now from this. If you extrapolate from this plate to the whole plate line, it's probably prohibitive. But if you say, okay, you have some scaling effects, and also we have learned a lot from, we have now the corporations also better in place where to put it. So yeah, I think.
We wait for the serial production. That's fine.
I mean, one thing we would not use this aluminum compound panel. They are relatively expensive, but we could also use traffic signs, which are produced in. I mean, it's always clever to use something which is produced in a big amount and which is easily available and fulfills the needs. And that's something we learned now. Relatively late, but this is probably a continuing process and would make it substantially cheaper compared to what we have now. The other thing, these prefab foundations are probably much cheaper than the foundations here. These were really quite expensive. And yeah.
We will know also more now when we install the one plate at the DLR side, because it will have some of the improvements already.
Thank you.
Okay, thanks a lot.
But maybe just a final word. I mean, if you really can achieve capacity gains, I think the gains are substantial compared to the investment costs. I mean, that should be a clear picture. But for that, we would be really need to be able, and we are not yet there, that we can bring additional capacity gains on top of pairwise separations. But if we can really show that, I think then we will have a relatively clear picture and will not depend on the details of the plate design, I guess. Okay, I think we have to move forward. We now had already part of the discussion that was planned afterwards, but that's fine. I mean, we can discuss it anytime. And now Andrei Koloshin will talk about use case 3 and the potential capacity gains that we estimated.
I think this is the Outlook presentation.
The FT presentation. The LRFT.
FT, okay. This one.
Okay.
Thank you.
Yeah, thank you. Yeah, my name is Andrei Koloshin. I've done this work mostly together with Dennis Fechtel. We both work at the DLR Institute of Flight Systems located in Braunschweig, Germany. I want to talk about the potential runway throughput increase. I guess you're taking monitor up there. So we've seen in the previous presentations already that plate lines are a method to enhance the decay of bake vortices close to the ground. And I want to talk about the benefits that we might actually gain from that in more detail. We've already seen one possible benefit is a safety gain if the plate lines are used for the mitigation of the severity of a possible wake encounter. Alternatively, if we maintain the same level of safety, we can also achieve a capacity gain by reducing the aircraft separation. And I will show some numbers about the possible benefits that we, at least for the moment, consider to be achievable with this concept. One very important question that's always asked during this discussion, the plate lines are only effective close to the ground, but what about the out-of-ground effect? If we are further up on the glide path, the plates are not effective there. What if we are reducing the separations not only in ground effect, but then of course also up on the glide? What's happening up there? And I will address this in detail. One important remark, sort of a disclaimer if you want to call it that way. We are looking at this from a scientist perspective. We'll do some calculations, present some numbers, but for establishing a corresponding safety case, of course, further investigations are required. And that's something that we should all keep in mind during this. We have seen this slide before. I don't want to jump too much into detail. Frank showed it already, but just as a short recap, so we can either increase the safety by using plate lines for faster wake vortex decay while maintaining the same capacity level, or we can also maintain the same safety level and then increase the capacity, or we can do a combination of both somewhere in between here. And mostly here we are focusing on using RICAD-EU and RICAD-EU pairwise separations as a reference, so we are somewhat in that area here. So I want to show the method that we used here in more detail. Generally, we followed the RICAD-EU and RICAD-EU pairwise safety case as close as possible. We did some slight modifications. I will go to that in detail, but basically we followed these safety cases. The evaluation basis were vortex measurements by LiDAR at Vienna Airport. Frank has already shown a lot of these measurement results. The datasets included measurements of vortices with and without plates for a variety of different aircraft types, mostly Airbus A320, Boeing 763 and Boeing 772, but also a number of other aircraft types. And the basic idea here for the in-ground effect calculation is to generate a generic decay curve for the reasonable worst case scenario for the vortex evolutions without plates at first, in analogy to RICAD-EU, and then fit this generic decay curve to the RICAD-EU curve.
And then also apply the same method to the measurements with plates so that we can combine these two decay curves. And when combining these curves, we see that there's some kind of time difference between those. And we can transfer this timing difference to the aircraft separation difference just by using the airspeed of the aircraft. I want to show some plots on this. So we are generating the generic reasonable worst case decay curve following this approach. On the left-hand side, we can see some measurements. Frank already showed quite a lot of data has been gathered. Here's just some example data from these LiDAR measurements. Here's plotted the circulation over the time span, or the vortex age in this case. And we see that we can fit that with a two-phase model with a slow decay at the start and at a certain time then a rapid decay is following. That's what we typically see in most of these data. And from all these measurements, Frank already said, quite a lot of data has been gathered there. We have calculated a median decay curve for all vortices that live at least 5 times our reference time. So here we are in dimensionless form for this generic curve, but we will see data with dimensions included again in the next slides. So we excluded the short-lived vortices here because very short-lived vortices are not relevant anymore anyway. And of course, we applied the same method to the measurements with plates then so that we can compare these two. And that's what we see on the next slide. Firstly, we see that this generic reasonable worst case decay curve from our measurements fits quite well to that from the RICAD EU safety case. So that's our curve without plates. And if we compare to the decay curve when we have plates active, or passive, but they're standing up there then, and we see that the wave vortex decay is enhanced. So the decay is a little bit faster, the circulation goes down faster. And we can transform that into a difference of the time. Here we are still on the dimensionless scale. It's our delta t star in that case, the time difference. And what we can already see here on this picture is if we have a look at the delta t at different points in time, if we start here, then we have only a small time difference at a small vortex age. And if we move further to the right-hand side for higher vortex age, we see a higher timing difference if we want to maintain the same circulation level here. And we can see it also in more detail on the right-hand side here. So at the start, we have no difference. And moving forward on our vortex age scale, then we see that we have an increase of the benefit of the time difference here. I want to give an example with detailed numbers, not in the dimensionless case, but now with proper dimensions here. So we have our 2 decay curves with and without plates. If we have a look at the RICAD EU separation, in this example, we have a Boeing 777 as the leader aircraft and an A320 as a follower aircraft. Then we can convert the separation from nautical miles to a time separation if we keep the airspeed in mind. And we have a look at the circulation level that we normally would get without plates. Then we can check at what time do we get the same circulation level with plates. And that leads to our timing difference that we can convert back to a difference in separation nautical miles by using the airspeed again. So that's a general method that we have used here to compare the measurements with plates and without plates. If we do this for all the different aircraft categories, firstly for the in-ground effect analysis only, then we come up to these results. We have been asked, why do we want the results up to 0.1 nautical miles? I want to address this question right away here. So basically, often in many cases, especially for RICAD EU pairwise, the rounding has been done to 0.5 nautical miles. And if asking air traffic controllers, they typically say when using only conventional air traffic control methodology without any kind of assistance system, then 0.5 nautical miles is a typical precision that seems to be reasonable. And for a safety case that might make sense, our perspective here is a scientist perspective. So we want to take a look at the numbers, and we decided to not round these numbers at all when storing them in our calculation. So we have the highest precision that we can achieve in our calculations in store. Just for the presentation slides, we decided to round them to 0.1 nautical miles, so we can give somewhat precise values without overflooding the slides here. Too many digits, but basically we decided to not round these numbers at all because we are looking at them from a scientist point of view. For establishing a safety case, of course, a rounding up to 0.5 miles could be done, but from our perspective, we want to see the precise numbers. And if we take a look at those numbers, and we can see in the top row the resulting separation for the IgE analysis only, so only in-ground effect on this slide. The resulting separation. In the second row, we see the separation difference when we are using plate lines. And in the third row, also in relative values. What you can see here, the absolute benefit starts at about 0.4 nautical miles and goes upwards to 1.1 nautical miles. And we see there's an increasing absolute benefit with increasing vortex age. That's exactly what I've already shown on the previous slide on the time scale that transforms to the scale here as well. If we have a higher overall separation, then we also gain higher benefits. But that means that the relative benefit remains more or less the same. It's somewhere between 12 and 15% for all the different aircraft categories. Yeah, MRS means minimum radar separation, but probably you're aware of that. So in some categories, we don't have any wake vortex separation, but only minimum radar separations. But for all categories where wake vortex separation is relevant, we get quite substantial benefits here for the in-ground effect. So that's for using RECAD EU categories, but we've also done the same analysis for RECAD EU pairwise instead. So we're not looking only at these categories here, but for 86 aircraft types, we have looked at all the possible aircraft pairings here. And we can see the results here. Basically, the numbers are in a similar range, but the spread is a little bit wider because we didn't group them into categories where the worst case for each category is determining the final result, but instead we have a higher spread when we look at each individual aircraft pairing. So it starts at about 0.25 nautical miles, but goes up to 1.27 nautical miles in some cases, especially when we have lightweight aircraft behind upper heavy category aircraft. That's the case where we achieve the highest separation benefit in absolute values. In relative values, it starts at 12.6 and goes up to roughly 24%. And the average is quite similar to before, between around 15%. So that's the in-ground effect analysis. But as I've told you already in the introduction, it's very important to keep in mind what is happening out of ground effect. When we're going further up on the glide, the plates are not effective there. So what happens if we are reducing our separations? And what we've done here is an OGE analysis without considering the effect of plate lines because they are not effective out of ground effect, and then combined the OGE analysis without the plates with the IgE analysis with plates in a conservative way. That means we take the higher separation value of these both cases, and that's our final result that I will show on the next slide then. And using this way, we can use the benefits from the plates without compromising safety further up on the glide where the plates are not effective. So what have we done here for the OGE analysis? We use the comprehensively validated P2P wake vortex fast time prediction model without the plates effect because we are out of ground effect now. Frank can definitely tell much more about this model because he has developed it. Also, we use the rolling moment coefficient, the RMC, as our safety metric. We use the same definition as it has been provided in the RECAD EU pairwise safety case. So we are trying to be comparable with the safety case. And we use the RECAD EU pairwise minimum separation for each aircraft type here as our reference. at an airspeed of a true airspeed, in that case 160 knots, as it is also given in the Recart EU pairwise safety case. I want to show you an example. I've chosen the Learjet 35 here, the example follower aircraft. It's a relatively small aircraft. That means we have a defined separation for all of our leader aircraft types. If I would use a bigger aircraft here, the example, then we would only have separations for larger aircraft and minimum radar separation in any case. That's why I've chosen a small aircraft here. And we see the separation start at about 7 nautical miles for the Airbus A380 in front, and then it goes downwards to 2.5 nautical miles for smaller aircraft. Here on the right-hand side, we have some small propeller aircraft that we also considered. I guess the most on the right-hand side is a Piper 34, if I remember correctly. That was the smallest aircraft that we considered here. So that's basically given the Recart EU pairwise separation for every different aircraft type. And what we've done here is we calculate the RMC values for all the different aircraft pairings. We actually see here for the A380, it's not the highest RMC because in that case the separation is much higher. So we are at a higher vortex age. That means that we actually have a lower RMC value. And the highest RMC value for this aircraft pairing using these models here was actually for the Boeing 739 in that case, because that's the largest aircraft where we still only a separation of only 3 nautical miles. So that was the worst case leader aircraft, if you want to call it that way. And we did this investigation for all different aircraft pairings. We identified the worst case leader, so that leader aircraft that induces the highest RMC at the Recart EU pairwise separation, and we consider this RMC value to be an RMC limit for the particular follower aircraft. And what we can do in the next step is then, if we can align all the RMC values to this RMC limit, then we have some potential separation benefit here in the Recart EU pairwise separation. So if we reduce our separation slightly, we can try to move the RMC upwards toward this limit value without exceeding it. And for this example case, we get the following values. If we have larger leader aircraft, then we can just reduce the separation slightly and we reach this RMC limit. If we take a look at small leader aircraft, then on this theoretical calculation, the result is actually we can go down to a separation of 0 and still not exceed this RMC limit, because if we put a small propeller-driven aircraft in front, and yeah, that's what happens. We don't need any wake vortex separations, but these cases are not important anyway in our use case here. So of course we look at larger, heavier leader aircraft with small aircraft behind. That's more important here, and we can align them on this RMC limit. We have been asked, what about the acceptance of aligning all this on this RMC limit? Of course, the encounter risk will be higher, and this is not the resulting safety case at the end, of course. We are just looking at it from a scientist's point of view. In the end, we will combine this OGE analysis with the IGE analysis, and then we see the finally resulting separation. But just to give an example, we see there is some potential benefit here for the OGE separation. And the way we look at it is, we have this benefit here, this potential benefit already available. It's there without needing any plate lines at all. We could theoretically reduce our OGE separations for many aircraft pairings without exceeding this RMC limit that we define by the worst case leader aircraft. But normally, for most of these aircraft pairings, the in-ground effect case is dimensioning the separation in the end, so that we cannot use this potential here, even though it's already there and we don't need plate lines for the OGE case. But if we can get some benefits in the IGE case, in-ground effect, then we enable using some of this potential here. But in the end, we will not align all the aircraft types here to this RMC limit, because in most cases the IGE effect is still dimensioning the final separation. But we can at least use some of this benefit without compromising the OGE safety. So that's the basic idea here. And if we do this and combine the IGE and OGE case, then we get these results here. First, I show it for the Recart EU safety case as a reference here. Also rounded to 0.1 nautical miles to not overflood it with too many numbers here. But basically, what we see here for super heavy, but that's only one A380 aircraft in front. Actually, in this case, we don't have any effect here because the A380 is actually the worst case leader aircraft for many of the follower aircraft types. In some cases, for other leader aircraft were the worst case leader. So in that case, we have slight improvements for the A380, but not too much. Also, the benefit is a little bit lower in this case because if we sum up the aircraft into these categories, then the worst case aircraft in each category is defining the separation for the entire category, and that's eating up a lot of benefit here. So we get somewhat smaller numbers, but we still see that the absolute benefit here is between 0 and 0.7 nautical miles in the best case here for small aircraft kind upper medium. And the relative benefit is between 0 and 14%. And if we only have a look at heavy behind heavy or medium behind heavy, which is the most relevant combination at many international airports, then we have an average benefit of at least 7.5% in that case. But we can further improve it if using RECAD EU pairwise as a reference. And I will show that on the next slide. So we've done the same analysis, but instead of taking into account the different aircraft categories, we take a look at all different aircraft pairings. Again, 86 aircraft types have been used here. And there we see that the range of the separation benefit is ranging from 0 to 1.22 nautical miles. So we have a slightly higher benefit. The average is roughly half a mile. And also the average percentage value is going up towards 13% roughly. So it's nearly double the value of what we've seen before, just because in this case, I guess it's clearly visible here. Our worst case leader aircraft are only these lines here, A380 for many aircraft. I guess the next one is Boeing 748, if I remember correctly, is our second aircraft in this list. So the worst case leader aircraft is reducing our benefit in some cases, but not for the entire category. And that means for all other aircraft types in the same category, we can gain some substantial benefits in the average of about half a mile or 13% when using RECAD EU pairwise as a reference. Okay, so with that, I want to come to the conclusions. So we have seen, even though plate lines are only effective close to the ground, they still support a potential reduction of the separation further up on the glide slope. We consider it as a reduction potential that is already there outside of ground effect, which normally cannot be used because the in-ground effect cases I'm mentioning it. But using the plate lines, we can reduce the separation in-ground effect and then can also use that out-of-ground effect without compromising safety. When using RECAD EU as a reference, we can gain substantial benefits only for a few aircraft category combinations, but these are the most relevant, so that is already some benefit. But especially when using RECAD EU pairwise as a reference, then we see that for most aircraft pairings we can get about half a mile separation reduction, and that's quite a substantial benefit. As a final remark, I want to address the topic of wake vortex transport. That's also very important and has to be kept in mind. We didn't consider it in these calculations here, but especially out of ground effect, it's a very relevant mechanism for establishing a safety case that definitely needs to be considered further, but maybe we'll talk about that in the discussion later on. Yeah, and with that, I want to thank you for the attention. Also, thank my colleagues, not only Dennis Fechtel, but also the colleagues from Oberpfaffenhofen supporting this work and the other coming here. Yeah, I guess we still have some time if you have any questions, or we'll step into the discussion then anyway in the next time.
We'll go start. One or two others. Yeah, time to ask a few questions. With this, we are through with the presentations. We just have another slide to show what's next, where we think we are going to. But I think it's time to ask questions.
There is a
to
question
Andre or also maybe to others.
From an external partner.
Okay.
Participants. So Daniel Nelson, please go ahead. You have a question?
Yes, thank you. Thanks very much for the presentation. Really interesting. I just and apologies if I don't know if you answered it directly, but is the efficacy of the plate lines, is it affected by the wind? Because of course, when you talked, I mean, earlier on, we were talking about pairwise separation. Of course, we're very interested in that development. I wasn't quite sure whether the effectiveness of plate lines is affected by the wind in any way. I know we talked about the strength of the plate lines in terms of fungibility versus in terms of fungibility and whether things may hit it and whether I don't know if the wind would affect it. But with the sort of turbulence effect, does it have a bearing on that at all?
Generally, for our considerations about the reduction of the separation, we did not consider wind. Also, we have seen that a higher wind case is helping avoiding wake vortex encounters. So actually the no wind case is more or less a worst case scenario. So that's why we considered the no wind case here as a reference. So we're using the true airspeed of 160 knots as a reference without any wind effects. So that's basically the same as the ground speed then in that case.
Yeah, I would like to add, when we analyzed the measurement data, we had wind thresholds for crosswind and headwind. And we were looking in particular at low wind cases with wind speeds below 2 meters per second, because these are the reasonable worst case conditions. The vortices are not blown out of the glide slope, and wind always comes along also with turbulence. So also the vortex lifetime is the longest. And so the blades are really designed for this long lifetime. If you have additional wind, this will also not only transport, but reduce the vortex lifetime. And the blade effect is still there, but it's not so visible anymore because there's another mechanism that also contributes to decay. I mean, that's something we also could very clearly see in the large eddy simulations that we did before the campaign, where we had this wind effect.
Okay, yeah, thanks for the clarification. So yes, you're considering it under very low or still wind conditions, and obviously more wind than the less vortices elements that you have to that the plate lines have to compensate for. Makes sense. Thank you.
Thank you.
Is there a variability in the wake strength depending on altitude or density? So if you are out of ground effect, that there is an altitude dependency somehow, or is that not the case? Or how should I view that?
Yeah, generally the wake vortex decay is faster in the ground effect case.
Yeah.
Maybe Frank can also give some more details on that, but if we compare the decay curve just for in-ground effect and out-of-ground effect, then we actually see there's quite a substantial difference.
So to what altitude can you say the out-of-ground effect is valid? Is that important? If you look at, say, the approach operationally, to what extent can
we think ground effect can happen for the biggest aircraft up to altitudes, or flight altitudes of roughly 100 meters, 300 feet. Basically vortex strength depends on the flight speed, which changes along the glide slope, but also on air density, which changes. And as Andre was showing, we had for this out-of-ground effect analysis 160 knots airspeed as an assumption.
Okay.
And a lower density, while close to the ground we have lower airspeeds, which are taken from the BADA database for final approach. And then decay, I mean, in ground effect, you have always a minimum decay rate, which is caused by the interaction with the ground, which can be faster if you on top have wind and turbulence. But the longest lived vortices theoretically are in a quiescent atmosphere. No neutral thermal stratification, no turbulence, and no interaction with the ground. That would cause the longest lived vortices. But these can just descend below the glide slope without being impeded at all. So they are not relevant for us.
Okay, yeah. And you mentioned a bit in the last slide about transport. Can you elaborate a bit on that? What's the issue there, or foreseen problem, or?
Yeah, basically, yeah, it was the conclusion slide, the last point there. Okay. So basically, the wake vortex transport, that is, yeah, generally two categories. The first one, Frank just mentioned it, the feedback vortex descending motion down below the glide slope. That's an important mechanism. Out of ground effect, and the vortices are descending below the glide slope so that the follower aircraft will not hit the vortex anyway. So if we calculate these RMC values, these circulation values, that always consider the case if we would hit the vortices, but if we don't hit them anyway because they are descending, then we could actually go to much smaller separation values there, theoretically. But there are some effects, Frank mentioned it in the first presentations, for example, in some atmospheric conditions, the vortices may actually move upwards again, and then we might still hit them. So of course we have to consider that case. And the second mechanism is the transport by the wind, for example, in lateral direction, just blowing the vortices away either side, or of course also upwards or downwards if we have vertical wind. But in ground effect, we don't have this descending motion, as Frank has shown in the first presentation. The vortices are just descending a little bit and then bouncing upwards again, so they can stay in the area of the glide slope, and that's a completely different case than for the out-of-ground effect, where the vortices can basically descend below the glide slope quite easily. And that's a very, not only interesting but important mechanism for the safety case. So definitely further investigations are needed on this topic.
I've got one question looking to Austro control, but first of all, thanks for the presentation and the slides and the details. The blade lines are installed and are in use. Do you gain benefits, speaking of capacity, in real life outside, or do you use the blade lines for safety gains? We heard a lot about separation reduction possibilities, but I'm interested, how do you operate it at Vienna Airport?
I take the question. We're not that far. We had a trial for the measurement campaign, so the plates are not there. And we had talks with the airport. We wanted to have that particular plate be located where it should be located in the practical future. That was not allowed by the airport so far. As it was mentioned, the administration is done and always legal and could place it there, but we are not allowed there. But it's proven that we can expect these capacity gains and of course the safety gains.
Okay. Maybe you allow one remark. Looking about the differences between IGE and OGE, you spoke a lot about arrival separation, and we already had conversation via email. Maybe there's a big benefit if you don't take in the close look the effect of arrival, but of departure, arrival-departure separation for crossing runway configurations, because there's a big effect on IGE, and you have no problems at all with the out-of-ground reduction. If I understood the last presentation right, OGE reduced the possibilities of IGE quite a lot. A lot of reduction, separation possibilities pop away.
Thank you very much for that valuable remark. We are really keen on deepen that discussion and see what could be done there. That's a very interesting application that we didn't see before you pointed us on it, but it's maybe not only for Frankfurt Airport a relevant setup. And so, yes, thank you very much.
One more question over there.
Okay. If I may, few points. In fact, just starting by what you mentioned. Today, when we apply separation or spacing, basically we apply the largest constraint. So we have surveillance minima, we have weight minima, or indeed in mixed mode, gap spacing. So of course, if you can reduce, in some case, the weight minima, the next constraint that you may face can be, for example, gap spacing in mixed mode. So that could be a way, if you have some margins in your gap spacing, which are then constrained by your wake separation, if you can reduce your wake separation, you can take advantage of more efficient mixed mode operations. So, but I don't see really a link between, I would say, the plate line or the mixed mode operation. It's a way of applying the most effective separation or spacing, and indeed, if you can take advantage of wake optimization, you can then, as I said, optimize as well on the mixed mode operation. And by the way, there are also some some tools that we have been working in SESAR and zero control, this separation delivery tool, this indication for the air traffic controllers that can help also to facilitate the application of these different separation, like time-based separation, that can also be in this. I want to add, in fact, two points to the presentation. Starting with a reminder that all these RICAT developments that has been made, RICAT EU and pairwise, is always based on a relative comparison between aircraft type regarding their wake generation and wake resistance. And so we did that indeed primarily in ground effect. We also look at out of ground effect that it was presented. But basically, if you go with additional reduction of separation out of ground effect, as it is mentioned here, you will definitely increase as well the exposure to wake encounter out of ground effect. That's automatic. If you reduce further separation, you increase overall the risk. The question will be, what will be the level of acceptability of increasing that rate of encounter? Because in that case, you cannot benefit of the decay plate. So in the pairwise, we came up with some estimation of this increase of risk. But if you align again everyone to the maximum, let's say, level, which is still can be encountered today, but tomorrow can be encountered more frequently. So it may have clearly an impact on basically the crew perceptions that you may encounter this wake encounter out of ground effect on the glide, which are also typically a bit stronger because the decay is a bit slower. So that's something to keep in mind. And the second point is indeed on this granularity of the separation in the RICAT pairwise. We came up eventually with a half-mile granularity. Originally, we also designed to the 0.1. It was mentioned that the half-mile was then also more easily applicable by the air traffic controller without having an indication or a separation tool. But there was also a question that came through the consultation about the granularity of designing wake separation at 0.1, in particular, again, to differentiate characteristics between individual aircraft types to that level of granularity. And so I think that's something that could also, or must also be taken into account if we look at this further potential evolution. But today, indeed, back on the RICAT EU and the question on safety, I mean, in Vienna, you operate RICAT EU for, I think, since 2020, if I remember, at the moment without the plate line. And if the plate line would be installed, in principle, based on what has been seen, the acceleration of the decay near the ground could possibly limit the risk of encountering wake near the ground, near the runway threshold. So that could be seen as a safety benefit in that respect. For the pairwise as well, if there is an intention to go to that in the future. But again, for the vicinity near the ground, and the question is for the out of ground effect.
I would like to add a thought to the second thing you mentioned, Frederick.
Yes.
For RICAT, you rounded up from 0.1 nautical miles, which was your technical accuracy, to 0.5 for good reasons. And if we would do that now on top, we would have twice such a conservative buffer. I think if we should do that, we should start with your fine granularity, do our also fine granular computation, and then round up, in order not to do it twice, in order not to add safety buffers twice that add up. So I think that's a way how one could deal with that.
That's indeed makes sense. Now the thing is, at the end, it's about discriminating between different aircraft types' behavior near the ground or even out of ground, because without going into the details of the technical aspect, but indeed there is the influence of some factors which are different between aircraft types, like the vortex spacing. We tend to do some assumptions in some case, but even out of ground effect, and maybe FA, we discussed that as well, that when you're at out of ground effect, maybe having the same vortex spacing value as an assumption is not that maybe fully realistic. So that's things that could be looked at as well. And indeed, at the end, depending on the assurance level that we have, we could go to maybe some rounding.
In your presentation, you had a delta T star analyzed, but I didn't get, was it the maximum between the two curves that occurs, or is there a particular process to get to this delta T star at a certain level, or that was not fully clear for me?
No, sorry.
Not both at the same time.
It was like 10 or something, I don't know.
Yeah, somewhere in front for the in-ground effect calculations.
Higher up.
No.
Higher up. Yeah, you have this.
Yeah, somewhere
Yes,
like
yes.
7 maybe.
Yeah, so what determines the delta T exactly here? Because I could imagine that lower there is a higher delta T star. So why is this one chosen and not the highest value?
So basically this delta T star is a function of time, T star in that case, because it's a dimensionless time, and this function is plotted here, delta T star over T star. And this one here is only an example. You can, of course, terminate at any given point. And as I've shown, we have a small difference here at the start. Actually, if we start at time 0, then the difference is 0. That's why we're starting here. And if we move further down the slope here, for lower circulation, we have a higher time difference for the same circulation level, and that's what we're seeing here.
Okay. Yeah, I get it.
And then for a particular aircraft pairing, you have to go to the vortex age that corresponds to the aircraft separation.
Mm-hmm. Okay. Yeah. And a more general question, maybe to you, Frank. Can you elaborate a little bit on if an airport would like to go this way, what is involved in terms of certification or national authority approval or documentation, or you have some experience now in that sense, so maybe you can elaborate a little bit on that. What have you encountered?
Thank you, Wilfred. This certainly depends on the use case.
Okay.
If you would combine the plate lines just with the recut EU pairwise separations, which will be approved this year and released, most likely, then we would have the smallest effort, and we could use all the material presented by Grigori and go to a national authority, and they could check that and say it's fine what was done in Vienna or in Austria. I think in Europe this is all comparable, or maybe they come up with a little detail that they might have changed, and you have to work on that. So that could go relatively fast. Leipzig Airport showed certain interest. We were already talking with the relevant authorities, a ministry, and they agreed with this view. So, and if you want to go further with your use cases, I mean, that would bring me to the outlook. We still have to do scientific work, and in the end, we have to develop a safety case that needs to be approved, and that's of course much more demanding, much more work, probably most likely more measurements with LiDAR. Mm-hmm. So probably we would have to go to install the plate lines, have an immediate safety gain, maybe in combination with recut, but to have additional gains, we probably would have to do local measurements and formulate a safety case with the benefits we're seeing on site, and get them approved either by national authorities or EASA. For that, I'm also not clear who is relevant.
Okay, thank you.
Okay.
Other questions from the audience?
Outlook mal zeigen?
Maybe?
Bitte?
Die Outlook-Folie?
I guess that was a nice segue over to the Outlook, because exactly the safety cases.
Ich war jetzt mit Outlook im Outlook.
Take over the Outlook.
I think we are not really tied to our schedule, so if there are more questions in the audience, I think we have time to answer them. We're going to lunch, but that they are not waiting for us.
Yeah.
But I wanted to prepare what's next. So we want to bring forward this runway capacity aspects of plate lines. This has been mentioned before, and we have currently in SESAR 3 a proposal which is termed Go Start, which is organized by NUTS. And Go Start stands for Green Optimization of Systemized TMAs and Runway Throughput. And this possibly today it will be decided whether this proposal was successful or not. Maybe it will be delayed. I heard rumors. It's not clear. I checked my email. The message is not yet there.
No breaking news.
But there we want to reach a technology readiness level 6 with respect to runway capacity gains. And there are two major steps. First, we want to make available all measurements from Vienna, which is a substantially larger amount of data, almost 9,000 approaches, 25,000 vortex evolution by processing them with methods of artificial intelligence. We have very promising progress made with that in our group. This is led by Anton, PhD student, master students. And with that data, we want to make a more profound analysis for our different use cases, and maybe already include safety considerations that would be required for approval. So we want to go, the question you asked, Wilfred, we want to go further in that direction as far as we can, but we're afraid if we want to really go beyond recut pairwise separations, we probably would need also more measurements. That's not envisaged in that proposal. Then you heard it already, a second plate prototype will be installed at DLR in Oberpfaffenhofen. So if anyone who can't join now for visiting wants to see it, Germany is closer, you're welcome. That will be installed in a few weeks, I hope. We will talk with Gunnar about the situation. And generally, I want to state that we are happy to deploy plate lines together with interest airports or ANSPs. And we talked about it, so the process would be simplified to install a plate line yielding immediate safety gains, then measure the resulting vortex behavior, and establishment of a tailored solution for increased runway throughput, so something out of our use cases tailored to the specific airport needs. We learned that all airports are very different. There are very special ideas in Frankfurt, and but there's potential with the plates, and we would be glad if that system that we developed for years really could help to optimize air traffic. Thank you.
Thank you.
Thanks. Okay. So then we will close the meeting.
No more questions online? Or?
No more questions online. Thanks to all external virtual participants. We will close the meeting, and I think there will be a way where we will provide the presentations and the recording of the meeting. And yes. Goodbye and have a nice day.
Yeah, we will send emails around where you can watch the recording, of course.
Okay. Thank you, everybody.
Bye-bye. Thanks a lot.
Bye-bye.
Thanks.
Take care.